Allora. Okay, guys at home, just information. Are you able to see my screen? The screen where I'm writing, actually, this one. Yes. Huh? Is it okay? All right, great. Just waiting for a couple of guys, and we can start. Oops. Actually, do you mind if I leave the window open because it's warm? It's complicated. Ay. Hi, no, ciao. No. If you don't mind. Okay, it's 2:05. 5 minutes, the academy 5 minutes. Should be mine, the 5 minutes. The academy 5 minutes are yours. But okay, that's okay. Before starting, actually, I apologize. I apologize because yesterday I was not able to. No, shut up. Yes, I was not able to upload my notes on Teams, but I promise that I will do it either today or at most tomorrow morning, because I do not have a scanner and I cannot scan in a PowerPoint way this thing. Okay, but I promise that I will put also the lecture of yesterday. So today we are starting with something. No, we are starting slow, and then we are doing something which instead is going to be a bit harder in the second part of our lecture. So, what was the main message of yesterday? The idea of mathematical modeling. The main idea of mathematical modeling. The fact that you should be able, starting from the observation, phenomenological and empirical observation of a phenomenon, to try to write in terms of an evolution equation or a set of evolution equations, which are describing the what we are called state variables of our problem, and the state variables when you are then solving the evolution equations. So when you are finding the solutions for your state variables, this should give you the way your system is behaving. Now, this should make clear one extremely important thing, that the very first step when you are trying to build a mathematical model, so the first step after that you did your observational part or your empirical part, the very first step is trying to isolate what are the state variables, because otherwise you don't know where to start for building your model. again, the state variable, how you are isolating these state variables should come from experience, so from phenomenology and from observation. What becomes then extremely important from this point of view is try to understand what is the observational scale at which you are analyzing the phenomenon. When I'm speaking about the observational scale, this means that I'm speaking about the fact that I should be able to understand if I have to treat my my phenomenon from the microscopical point of view, from the macroscopical point of view. There is also a third route, which is the mesoscopic point of view. So the idea is that you should be able to identify one of these scales. Well, there are broadly these three scales, but of course there are always gray areas among them. So there is a macroscopic description, a macroscopic description, and here in the middle, let me also go to the mesoscopic one. So, why this is important? Because when I have a system, suppose that I'm trying to model some system. Now, should I model taking into account the description of the single particles, of the single components of the system? Should I instead try to understand what happens on average, on averaging the sum of these properties on some bunch of particles? Imagine that I have 1 million of particles. Should I really write down equations for following any particle? Should instead I write some equations for following the average quantities of a bunch of particles, so groups of 100 of particles? Or should I instead try to understand if it's possible to average on the whole system, on the entire system, and then to consider this 1 million of particles as just one entity? This is the idea of describing system in a microscope, approaching it with the macroscopic description, with the mesoscopic one or the macroscopic one. So the typical example, again, is the one of the gas of particles, which is in a container. From the microscopic point of view, as I told you before, what you're doing is taking each particle, each single atom of gas that you have in the container, describing its dynamics with some differential equation, and then try to solve the millions of equations that you have, eventually coupled equations that you have, because they are coupling through interactions between the particles. Once that you solve these equations, you should be able to do some kind of averaging operation in order to find some results, because of course you cannot present to somebody a result of 1 million of the dynamical evolution of 1 million of particles. On the other side, instead, you have the macroscopic description. Macroscopic description for the gas of particle, well, you know, instead of describing every single particle, what you are doing, you are describing the gas which is in the container through some few parameters. The density, which is barely telling you what is the number of these particles per unit volume. The temperature, which is more or less giving you an idea of how much these particles are moving around, and so forth and so on. So, from the macroscopic point of view, instead, then you are describing this bunch of particles as a whole system. The third route, the mesoscopic one. The mesoscopic one is a bit tricky, because the idea is that you are describing using the microscopic model, the dynamics of interacting particles, so interacting individuals. Once that you have described this thing, what you are doing is to use some suitable momenta that you can build up out of the quantity that you have been able to extract from the macroscopic description. So you're using these suitable momenta, which is going to be weighted over the statistical distribution for each microscopic description. So you will have some microscopic description of your system with some statistical distribution of these descriptions, and you are going to weight on top of these statistical distributions the momenta that you have been able to extract from information of particles. Now, typically, yes.
Can you repeat it, please?
For the mesoscopic part.
Yeah.
Okay, the mesoscopic part, in very few words, basically you are starting with describing with the microscopic idea your system, and then what you are doing is some kind of statistical analysis, well, an analysis taking into account the statistical distribution, the statistical probability of a particular microscopic condition to appear. So you have your bunch of particles. You are initially describing these particles from the microscopic point of view, and then you're trying to understand statistically these things, how it's going to behave. I will give you an example which is a bit complicated, but it's an interesting one later for the mesoscopic approach, because probably this is just a blah blah blah, but with the example it's going to be easier to understand. So there is actually an extremely important distinction for the mathematical model that you should be able to build with the microscopic description or the macroscopic description, and that's the following. Usually, the evolution equations that you're able to write down in the microscopic description are usually ordinary differential equations. So whenever you find a system, mathematical model, which is described in terms of ODEs, it's almost sure that what this system is describing is a microscopic system. On the other way, with the macroscopic description, usually the world is described in terms of PDEs, of well, system of partial differential equations. Okay, so ODEs for microscopic systems, for the microscopic description, and PDEs for the macroscopic description. For the mesoscopic one, again, we will see later an example of how things work. Watch out, there is a very, very important point here regarding the words small and big, small and large. So a system that can appear large in a certain context can of course be small for another context. If you are considering the system, the sun, if you consider the sun as a star which is made of an incredibly large number of particles, well, this of course is going to be a large system. Now take the sun, put the sun into our galaxy. Actually, the galaxy can be considered as a gas of stars. Okay, so you forget about distances which is between, which are between the stars. So you are considering stars as if they were particles of a gas, and this gas is in a container which is given by, well, the space where the galaxy is. Actually, if you are going on even larger scale, you can consider single galaxies as single particles in the big container which is the universe. So you can consider the universe as a gas of particles, and these particles are your galaxies. So of course, in this case, the galaxy is, if you are describing with a single galaxy, you are describing with a microscopic description the big system, which is the universe. But if you are considering if you are downsizing and instead trying to understand some dynamical inside the galaxy, or even more downsizing, you are considering dynamics of particles inside your star. Well, of course, this system are changing the definition, the idea of what's small and what's large. Now, let me start then with a first example, which is I'm reviewing the other time the case of spring with the mass which is attached to the spring, but in this case I'm considering a case in which I also have friction. Okay, so I have the wall and this is the ground. So this is my spring. This is gonna be my body with mass m. So the if I didn't have the friction term, this would be described by the usual Hooke's law. So m squared x in the t squared equal to minus kx. Then I'm adding the friction term. The friction term, I'm supposing by observing the system, that is a force which is proportional to some power of the velocity, and with the sign which is opposite to the velocity, because of course it's a force which is going against the movement of the body. So written in mathematical formula, this means that I can add a term here which is going to be like minus some, let me write some constant c times the velocity to some power p. Now, again, as we have seen yesterday, do you remember what was the state variable, the state variables that could describe this system? So yesterday we defined some vector u, whose components were a u1 given by x, and the u2 given by dx in the t. So one was the position, the other was the velocity. I'm doing the same now, so I'm again splitting into these two state variables. The problem, why? Because what I want to do is to take these second order differential equations and to translate it into a system of first order differential equations. So in order to do this, what happened here is, well, the first equation, which is the trivial one, is du1 in the t is equal to u2. Okay, so it's too small. And the second equation is going to be du2 in the t equal to minus k over m u1 minus c over m u2 to the power p. So, few observations about this system. First of all, this is a system of coupled first order ordinary differential equations. The system is non-linear. Why is non-linear? Basically, it's non-linear because in the second equation, there is this term here. Actually, saying that it is not linear is not exactly correct, because, of course, you can reduce this system to a linear system in two cases. What are the two cases? In which case this system is linear?
If P is 1.
If P is 1, that's one case. The other is trivial. P is equal to 0. Yes. So for P equal to 0 and P equal to 1, this system reduced to a linear system. Otherwise, it's non-linear. What can we still say of this system? Well, actually, reduced to the linear case also if C is equal to 0. So if C equal to 0, of course, this means that you do not have the friction term, and if you don't have the friction term, we know that the system reduced to the standard linear system. Is the model consistent?
Yes.
Why? There are the two variables, yeah, because this is a resume of yesterday's lecture. The system is said to be, a mathematical model is said to be consistent if the evolution equations that are describing the models are in the same numbers of the number of state variables that are describing the models. Do you think that this is a microscopic description or a macroscopic description of the system?
That's a macroscopic.
That's it?
Macroscopic.
Macroscopic. Why?
Because I'm not taking into account every single particle of the spring or the mass.
Well, actually, my mass here it's a test mass. It's a point mass. So I can well, it's this. And the spring, don't consider spring. Spring is some object without mass, without anything. It's just giving you some force. So actually, this should tell you that this is a microscopic description.
Related.
Huh?
Related for M.
What?
Maybe macroscopic, maybe microscopic.
This is no. This is microscopic, but there is actually a very simple trick which allows you to say that this is microscopic description. The equations are ODEs. So as I said, when you have ODEs, it's almost sure. It's not almost sure, but it's almost sure that the system that you're describing is the description that you're using. It's the microscopic description. Okay. Whenever you have instead PDEs, as we will see in a moment, instead the description that you are doing is a macroscopic description. Let's see what happens. Right, so suppose that we are then reducing another time this system to the case without friction. So let me forget again of this term here. What happens if the elastic constant, the K, the constant which is describing the elastic force, depends itself on some state variable. So for example, what happens if K depends on, in this case, on the position, on X. So let me suppose that K depends on X, which basically means that K depends on U1. Let's suppose that K depends on U1 with some law which is given by K naught times a power law, U1 to the power Q. So if I have this kind of law, then what I would have here, it's again something that I can write as minus K naught over M, and then this one is U1 to the power Q plus 1. So what we obtain is, again, it's a system which is nonlinear. So the nonlinearity is not necessarily connected with the fact that you have an external force or a friction force or something like that. And nonlinearities could be connected, could be related to the fact that some parameters of your system can have a non-trivial dependence on the state variable. In this case, what we have done is to kill completely the friction force. So I forget about the friction force that was the source of nonlinearity in my equation. But instead, what I've done is to introduce the nonlinearity now in the system through another way, which is, what is the other way? The other way is to consider k, the constant k, as depending from one of the state variables. In this case, depending from the position, point 1. Okay? Great. So this complete the first example. Let's you can ask. If you want to ask, you can ask. I mean, I'm here for this reason. Let's consider the second example. So the second example is a model. Is this working? Yeah. Okay. So the second example is the example of a diffusion model. Actually, it's a pollutant diffusion model. It's a model which is telling you how a pollutant diffuse inside another fluid. Okay, so pollutant inquinante, diffusion. Then suppose that I have this pollutant and that I introduce the pollutant. Wow, this chair. Introduce the pollutant in a canal, in a tube, a pipe, in the x direction. Okay. The physical quantity, remember, the first thing that I have to do is to identify some quantities of physical quantity of which I want to understand what's the evolution. Because if I define the quantity, then I will be able to eventually to understand how I can use my knowledge from physics, chemistry, mathematics to build up the model. In this case, the physical quantity that is going to describe the state of the system is the concentration of the pollutant, okay? Which I will write as C of T and X. Note that I'm assuming that the variations of the pollutant in the y and z direction are negligible. All right? So the concentration of my pollutant is changing only in the x direction. It's not changing in the perpendicular direction, in the orthogonal directions. So this is a function of T naught T times, let's say that my tube is 0L. In R plus, okay? Real positive numbers. I cannot have a negative concentration. Does not have any meaning from the physical point of view to have a negative concentration, okay? Yeah. Then let me go rho naught. This is gonna be the density of the pollutant. Now, first ingredient. Second ingredient. I'm starting from the assumption that there is no leaking on the walls. So basically, the pollutant is not leaking toward the wall. The pollutant is always inside my tube, my pipe. This also means that basically, lately, when we are going to use our usual conservation equation, the flux that I'm considering is the flux which is coming from a section of the pipe and going outside from the other section of the pipe. I cannot have any flux from the walls of the canal, of the pipe. And then the third condition is that the fluid is steady. Okay. Then why I'm using this assumption? Actually, I'm using this assumption because this is a simplifying condition to understand what can be the behavior of the pollutant inside the fluid. Because indeed, then I know that, I don't know, but I can observe this and try to catch a phenomenological law to understand what is the velocity of the pollutant then inside the pipe, inside the fluid, inside the pipe. There is a phenomenological law for this, which tells me that the velocity of the pollutant is going to be proportional to the gradient of the concentration, and is going to be proportional to 1 over the concentration, so inversely proportional to the concentration. Now, what I can do is to put together these two informations, and what I can say is that I can write the velocity of the pollutant, which is diffusing inside the fluid, inside the pipe, as 1 over C times the gradient of C times, let me add this minus 8 naught, this constant, that will be useful later. Now, what I have to do is, again, what I want to find is an evolution equation for the concentration. And in order to do this, what I would like to do is to find this evolution equation using some conservation equation, some conservation law. So you remember, because if I'm using the conservation law, I already know what's the scheme that I have to adopt. The rate of change of my state variable, so loosely speaking, the derivative with respect to time of C, is going to be equal to the amount of pollutant which is created or destroyed inside the pipe, plus the amount of pollutant which enters which flow inside the pipe, minus the amount of pollutant which instead go out from the fluid and from the pipe. Now, in order then to describe this model using this idea, what I can do is, what I have to do is to define, first of all, a flux of pollutant inside the fluid. So let me define Q of T and X. This is the flux of the pollutant the pipe. Then let me call Q plus and Q minus These are the ingoing and outgoing fluxes. Now, usually in this kind of problems, you are always starting from the assumption that your function are nice functions in the sense that they are functions that behave. They are smooth functions with eventually continuous first derivative, and eventually they are also higher derivatives are continuous, and so on. Of course, this is not always assured, but most of the problems allow you, most of the problems in mechanics and heat problems allow you to, diffusion problems allow you to use this kind of simplification. Then, if my function q is smooth enough, and if q is continuous with the first derivative continuous, I can write q plus in terms of q minus. Do you have any idea of how to write q plus in terms of q minus? Actually, this is exactly the same thing that we did yesterday when we were considering the heat equation. So you remember, when we were considering the heat equations, what we had was the flux of heat through the surface, right? So I was considering the integral on the boundaries of q times n. Please.
K, constant K. Time is dk.
Constant k times?
Not d.
But it's not going to be a constant there.
Derivative.
Eh?
K time is derivative of temperature in case.
No, wait. What you're saying, this is a constitutive equations. No. I'm not speaking about the constitutive equations, which is relating the flux to temperature. I'm not thinking about the temperature. What I'm saying is another thing. If you remember, we described yesterday the flux of heat, which is flowing through the surface, as the integral on the boundaries, on the boundaries of the volume that you're considering, of the flux q, x, and t, scalar n, where n is the normal to the boundary in the S. So if you remember, this is equal by the divergence theorem to what? To the integral on the volume of the divergence of q in the x, right? So basically, this thing, if you are studying a system which is instead in one dimension, would give you some law here, some equation here. Basically, what you will have is q plus equal to q minus the q, the x in the x. You can see this in a very simple way, in another way. Look at this. So I can consider the flux at a certain point. So the flux which is entering, suppose that I have a tube. Then the flux is entering here in A, and is going out here in B. Okay? So the Q plus is going to be Q of A at time t. Q minus is going to be Q in B at time t. Okay? I'm putting Q minus on the left hand side. This is the reason of this minus. Okay? All right, what is this? I can rewrite this as minus the integral between A and B of the Q of x and t in the x, the x. There was a no. Why no? Who said no? my body. All right. Okay, so basically, imagine to take this formula and to consider extremely short distance between the so to consider a small volume of the pipe. So you are considering Q plus and Q minus to be the ingoing outgoing flux for a small volume. What you obtain is this formula here. That's actually this one. For this would be, just a second, delta Q equal to minus the Q the X dx, where this delta Q is Q plus minus Q minus. Yeah.
But the as its area, which should be X times the.
This is in one dimension for the moment. I'm just considering in one dimension, the one-dimensional part. Yes, in order to consider then the flux, which the total flux which is passing through the area, then through the pipe. Sorry, I should multiply both sides by the area. But I'm doing the assumption that the pollutant does not change. The pollutant and the flux of the pollutant does not change in the direction which are orthogonal to X. So they are not changing in the direction Y and Z. That's actually why here it's a one-dimensional problem. Okay, so to wrap up, this tells me that I can write. Let me write again this formula: Q plus. So the ingoing flux is equal to Q minus the outgoing one, minus the Q in the X times the X. Now, here, that's where another time of phenomenology comes in, because fantastic, beautiful as you want, that's a nice formula. But that's exactly the same problem that we had yesterday when we were trying to find the formula for the equation. Because you remember yesterday, at a certain point, we had this formula with the total internal energy of my system expressed in terms of the flux conducting. But how can I relate the two things? I have to find the third state variable, in that case temperature, with respect to which I should express my quantities. In this case, I already identified what is the state variable. It was the concentration. So what I want to do now is, in order to find an equation, an evolution equation for the concentration, I have to find a way for expressing the flux in terms of the concentration. And this is actually a phenomenological law. Again, what I have to do is to go there with my experimental device and try to understand how can I relate the two things. This has been done by a guy whose name is Fick. So this is the Fick's law, which states that the flux of the pollutant, Q of X and T, is equal to minus D, which is what is called the diffusion coefficient, diffusion constant, times the, well, you should have here the gradient of C. Let me write this as dc in the X, because as we have said, we have just, I'm reducing the problem to the one-dimensional case, in the sense that in Y and Z, I don't have changes in the concentration of the pollutant, neither in the concentration of the pollutant nor in the flux. This means that I can use this formula here, which is actually another phenomenological formula, but we will show that basically are extremely related to each other, to express the flux in terms of the velocity of the pollutant inside the fluid, inside the pipe. So if I'm using V equal to minus H naught over C times the, well, the gradient of C is going to be the C in the X. This tells me that I can rewrite Q of X and T as what? As velocity of the pollutant times the concentration of the pollutant divided by H naught and multiplied by the diffusion constant. Okay, so luckily enough, then we have some constitutional equation. So it's a constituent equation. Sorry, it's an equation which is relating Q to C. So what I can do now is finally to write down the conservation law. So the conservation law, which should tell me how does the total concentration of the pollutant is changing in time. So what I want to do is to calculate the derivative with respect to time of rho naught times C times the elementary volume, A the X, where A is the section of the tube. So this is telling me how much the pollutant is changing in time in the elementary volume. And this guy here, well, I can rewrite this as rho is constant, so it's rho naught derivative with respect to time of the concentration times A the X. So this guy here must be equal to what? To the total incoming flux of pollutant inside the pipe, which is going to be A times Q plus, again, because as your colleague was saying, actually, in this case, you have to consider the fact that the tube with the pipe has an area equal to A, so this flux should be multiplied, the flux per unit volume, per unit surface should be multiplied by the area to understand what is the total flux incoming in the pipe, the total flux of pollutant incoming in the pipe, minus the one instead that's going outside. So it's going to be A plus minus A Q minus, which is A times Q plus minus Q minus. But now what I can do is to use this equation here in order to substitute Q plus minus Q minus here. And what I found is A, which multiplies minus the Q, the X in the X. And now what I can do is to take the formula that I found, which relates the flux to the concentration. So what I want to do is to use this formula and to substitute this formula inside the equation. So I will get A times minus the derivative with respect to X of V times C times, let me put it outside, D over H naught, the X. But it's kind of magic. The over is not the x. Okay, this is a C. Now what can I do? Well, I can use now the expression that I have for V. And remember that I have this expression for V. Okay? So let me use this expression. What I found then is, so I substitute here V. I find, this minus times minus is plus, so I have A times D over H naught multiplied by H naught. So this simplifies H naught, H naught. And then I will add D in the X of what? Of 1 over C times the derivative with respect to X of C. 1 over C derivative of C with respect to X times C. So this C and C simplifies. And this becomes A D the squared the X squared of C. Again, since the volume that I'm considering is a completely generic volume, what I can do is to simplify the A the X in both sides. So this thing here, this thing here, which cancel this thing here. And finally, what I get is this fantastic equation with which we will have a lot to do during this year, which is the C in the T minus D over rho naught times the second derivative of C with respect to X equal to 0. So this is what's called the diffusion equation. And I invite you to compare this with the heat equations that we introduced yesterday. Okay? Now,
sorry, but why we simplified the A and the X?
A the X here and A the X there, because actually these things should be then integrated over the volume of the over the volume of the pipe. But in any case, you remember that also yesterday when we get a final equation which was an identity between two integrals, then what you can say is that the volume is completely generic. Also in this case, the volume, you can take a completely generic piece of your pipe, of your canals, and you can simplify the integrals over the volume. So I can write this thing in an integral form, and with the same ideas of yesterday of just considering the integrand to be equal. That's why I'm simplifying here the A X. If you want, you can also see just simplifies on the left hand side, the right hand side, the same terms, the same factors. Actually, it's you see, I simplify this with this.
Thank you.
Now, I would like just to comment another thing before taking a pause, which is the following. So, suppose now that instead that you have a velocity of the pollutant which is depending on the concentration. So this means that the velocity of the pollutant, I want to write the velocity of the pollutant as minus h naught over c concentration times the c in the x, and this is the usual law which is describing the velocity of the pollutant as function of the concentration. But now I want this to depend also in nonlinear way from the concentration. So I'm multiplying by a factor h of c. This h can be confused with this, but no, it's okay, it's fine. Such a way that I have an extra dependence here inside from the concentration. Okay. So what happens if I'm doing this? Of course, what I'm changing now is this right-hand side of the conservation law, right? Why? Because now I have to pay a lot of attention when I'm doing this derivative here, correct? Because now what I have is d over h naught times the derivative with respect to x of v times c a dx. Let me substitute the function b, which is this one. So this quantity here is V, the new V, the V which depends in a nonlinear way from the concentration. Then this is multiplied by the concentration itself, because it's here the factor C. So H naught simplifies. This C simplifies with this other one. What's the problem? The problem is that while before, without the h of c, I just had the first derivative of c, such a way that then this derivative outside was just acting on the first derivative of c. Now instead I have two functions. So what I will have is d, which multiplies, the hc times the second derivative of c with respect to x. And then I have the extra term, derivative of h with respect to c times the c in the x squared. So again, this is a case which enters another time in the kind of examples that I was showing you before of nonlinear equations, nonlinear systems, which comes from the fact that where the nonlinearity comes from the fact that it's one of the parameters that can supposedly be constant, but in this case is not constant and depends on the state variable. So while in the simplified case hc is equal to 1, in this case hc is a function, is an integral function of the concentration c. And this fact introduces a nonlinearity in your problem. Then, of course, what you can do also is a kind of generalization in higher dimensions. In the case of a generalization to higher dimensions, what you will have is a generalization of the diffusion equations with the introduction of the Laplacian C, because of course instead of having just the second derivative of C with respect to x, you will have the sum of the second derivative of C with respect to x plus the second derivative of C with respect to y plus the second derivative of C with respect to z. This is some trivial generalization that you can find also by your own as a good exercise. And I will stop here for some minutes because the next problem is, I think, a bit complicated, and it's better to be more fresh.
The final equation, is there a minus before the D?
Actually, it's possible that in this expression here there is a minus, some minus sign.
Yes, it's.
Actually, there is a minus here that I didn't write here, but I don't care because then when, of course, when I'm taking this expression and cooking in the conservation law, I should pay attention to the fact that there is an extra minus that I have. Yes, in principle, should be like that, like that, like that. Okay? And then you can straightforward evaluate. But in any case, again, just calculate. What the important thing to calculate is this quantity here. I don't care about numbers which are outside. But this is more interesting, eh? The next problem is going to be more interesting. The next problem is going to be a problem of bumblebees. Carbon.
Stop. Stop.
Che appena sveniremo una pausa caffè di una classe che sto dando os meus parentes não são sabemos. Pois é, nada, mas falaremos com certeza. Fiquei super surpreendido desta coisa de mudança para repente. Aliás, já falámos que querias mudar, mas não pensava que querias mudar tão rapidamente. Pronto, gosto da ideia porque necessitavas também um pouco precisavas também um pouco de cambio mental, mas fiquei sempre no mesmo espírito. Mas em sério, há balada. Sabes o que é bom na balada? É que até quando estava lá em Portugal, que estava lá em Lisboa, faziam muitas publicidades da balada. Ou André, a Meroxi, André David, sabemos deles. Eles viram lá e sempre disseram que depois de mudar ficaram super contentes porque é um bairro muito bairro de vida de barrio. De vida de barrio como era o resto. Então fiquei super contente que elegeram, escolheram a balada para ir lá viver. Bravo, bravo. E para nós, sim, temos, porque não a fizeram? Não a fizeram porque ainda estou à espera do contrato. Depois eu confirmei com este gajo y nunca se parece un poco que está, que vive en las nubes. Mas ya dicen que ya refugiato e ainda non dio, e por isso estou a esperar. Bom, a Lucia está tranquila. Tchau, vamos ver. Dai, um abraço. Ascoltate, ho bisogno di un'informazione. Credete che sia troppo triviale? Volete un corso che sia più complicato? O, a parte il prossimo problema che sarà complicato? È troppo triviale, volete qualcosa di più, cioè sono cose che avete già visto in...
È molto triviale. No, scherzo. No, va bene, cioè, non sono problemi così, non ne abbiamo affrontati alla triennale.
Il prossimo ci scommetto che non l'avete affrontato.
Forse un po' meccanica razionale, ma
Poi meccanica razionale, ma proprio...
non così, diciamo. Era più...
Vabbè, in realtà sarà un corso che è abbastanza diverso da meccanica razionale, perché...
C'era un esame a scelta che era modellazione della dinamica, che c'era qualcosa di simile.
Allora, ti assicuro che sinceramente, infatti, quello che avrei voluto fare io è un corso che è più legato ai sistemi dinamici, perché secondo me la cosa più interessante anche dal punto di vista della ricerca adesso in modellizzazione matematica è in sistemi dinamici. Quando vedete alla televisione tutte queste cose di modelli epidemiologici, tutte queste cose qua, cioè, però... Boh, in programmi erano già scritti, quindi posso cambiare, ma non è che posso cambiare così tanto il corso, dai. Non posso, appena arrivato, posso dire, ma sì, rivoluziono io il mercato. Però, siccome...
Non sono comunque cose da mistero.
È che siccome non ho mai avuto a che fare con studenti italiani, vengo da fuori
No, ecco, sono cose nuove.
perché io rimango comunque del parere che cioè, in media l'università in Italia, un corso in Italia è mediamente più complicato che un corso all'estero.
Sì, per pareri moltissimi.
Però anche se pensi quelli che venivano da fuori, tipo la ragazza della spagnola.
Sì,
Ecco, infatti, guarda, io ho insegnato in Spagna, in Portogallo, in Inghilterra e in Giappone. È un altro livello, cioè si dimentica proprio.
Perché mi fanno a crocette, cioè tipo stile...
A crocette.
Mezzo americani mi sembrano, no?
Vero, verissimo, verissimo. Cioè, non sono tutti quanti così, cioè in Portogallo si sono lamentati per questo perché il mio esame non è un crocetto. Sfida tutto. Okay. Everybody inside? Yeah. Then we can start with the second part. No. We can start with the second part of the lecture. In this second part of the lecture, what I would like to do is an example of a problem in the mesoscopic regime. And if I have time, and I hope that I have time, I will talk about dimensional analysis. But it's something which is, dimensional analysis is something which is quite trivial, so I'm quite confident to be able to finish on time, even 10 minutes before, or 20 minutes before. Okay, next problem then. The problem is a problem of population. Hello? Population dynamics with stochastic interaction. Now, consider for the following, that if you remember yesterday, I told you that I'm following the book, the notes, lecture notes by Bellomo. But I also told you that sometimes I should to change the discussion on that book. This is one of these situations, because the discussion of Bellomo is not precise. It's at certain point is showing a result without saying anything. So what I will follow instead is the approach of the original scientific paper by these two guys, Jagger and Segel. You can find the research papers online. I don't know if you ever tried to download a research paper. If you are not able to download this research paper, well, in any case, I will post my handwritten notes, which are with more passages than the scientific paper. If you are interested, you want to download the scientific papers and you are not able to do that, let me know. So this is a paper published in 1999, the journal, I don't remember, but it should be Journal of Applied Mathematics. So I don't remember what's the title of the paper. It's not population dynamics with stochastic interaction in any case. So this is a model, as I was saying to your colleagues before, which is a nice model that can adapt to many systems. In particular, these guys, Jagger and Segel, developed the model to understand the behavior of bumblebees, Calabroni, of bumblebees when they were meeting each other while they were taking food in the flowers. Okay, but it was that the same model has been generalized in order for well. It has been shown that it's useful model for other kind of beasts and insects and all these things. But most importantly, it has been generalized for understanding some dynamics for the evolution of tumor cells. Okay, so that's a quite important, nice model. Now, what is then the idea? As I told you, this is a kind of model which is using then this mesoscopic approach, this mesoscopic description, which again, loosely speaking, means that I'm starting with the microscopic description of the system, and then in order to find some results, I'm passing to a probabilistic interpretation of what I discovered from the microscopic part. So the first thing then that I'm doing is to describe the microscopic state of each individual with a variable, let me call this variable x, which is in an interval 0, 1. So this variable is the variable which is describing the main property of the individual. So if you are considering, for example, this model as an application to tumor cells, this x between 0 and 1 is telling you at which stage is the cell with respect to the tumor. Okay? We can describe the level of activation of immune cells. Well, it describes, this is the equivalent of the state parameter that we were considering before. Then the second ingredient, the second thing that we will take into account is the statistical part, the statistical description. Statistical description. So I will call f of x and t in the x. This is the fraction of the population that I'm considering with a state in the interval x plus the x at time t. So imagine that I'm starting with this large population. I'm considering a tumor, right? I'm considering some piece of tissues, and I'm considering a tumor on top of this piece of tissues, right? I will have an incredibly high number of cells. This number of cells will be some number that I will call later C. Okay. This f of x and t in the x is telling me what's the fraction of cells which are at stage x, which has a stage between x and x plus the x of the tumor. Okay? Now,
so if the cells are all equal, f is 1.
If, well, actually, you can say another thing. If you are integrating, because you can normalize this f. So basically, the integral between 0 and 1 of fx and t in the x, it must be equal to the total number of population, actually. So if you can normalize in order to have also the population equal to 1, if this is your questions. Okay, but in general, if all the cells are equal, so of course this thing, since it's a fraction, is going to be 1. Yeah, right. Correct. Yeah, sorry. Yes, sure. Then let me call eta of x, y in the t. This is the probability of interactions of two individuals with one with at the stage x and the second one with the stage y. And that happens in a time included between t and t plus the t. So in order to understand what does this mean, probably with 2 more senses it's a bit difficult to visualize. But if you're thinking about insects, if you're thinking about the population of bumblebees, okay, this is basically this eta of x, y in the t tells you that the probability of that a bumblebee in the stage x can meet a bumblebee in the stage y in the interval time between t and t plus the t. This is the probability of encountering. But for specific individuals, which has a stage x with another individual which has a stage y. Of course, what if I ask you, what is the probability of no encounters? So this is the probability of encountering somebody. So if I have a stage x, this is the probability of encountering somebody with the stage y. If I want the probability of not encountering anybody, this would be equal to 1 minus the probability of encountering somebody. So eta x and y the t. So this is the probability no encounterings. Now, let me define now another probability. That's this psi of x, y, and u in the u. What is this? This is the probability that in a meeting between an individual with stage X and an individual with stage Y, the individual with stage X changes its state to a state which is included in U plus the U. So let me write, because this is probably a bit, no, this is probability that after an encounter, an encounter of X with Y, X changes its status to some state, to some state in the interval U plus the U. Okay? I don't know if it's clear. Let me repeat again. Okay. So imagine that I have this population of whatever beast of bumblebees. Okay. Any bumblebee has some stage. Some state. This state basically is telling you, for the case of bumblebee, eventually what is the trip that is doing on the flowers for having his lunch. Okay. Now it's meeting another bumblebee. Okay, so the first bumblebee has a state X, the second bumblebee has a state Y. So the probability of this encounter of the bumblebee X with the bumblebee Y is given by eta. Now, once that these two meet each other, one of the two can change state. Why? Because imagine this bumblebee that was eating in this direction and then cannot eat anymore this direction because meets this other guy. Okay, so this is the idea of change of the state. So the probability that the bumblebee X that meets the bumblebee Y change to the state U, well, to a state which is included between U and U plus the U, is given by this function psi. Okay? So X, Y meets, X changes to a state which is included between U and U plus the U. What about this? What about this quantity? How much is it? No? So this is equal to 1. Why? Because basically this is telling you what is the total probability that when X meets Y, change to some status U, to some state U, which is included between 0 and 1. But all the states of my system are included between 0 and 1, because this is by construction. By construction, all the states are included between 0 and 1. So I'm integrating here. When I'm integrating here between 0 and 1, since means that I'm basically considering all the possible changes of x when encounters y, and of course this probability of changing to any state between 0 and 1 is going to be 1, because x is going to change to whatever state between 0 and 1. And this is something which you should have expected, because this is just a normalization of the probability of this transition. Now I will define another probability. Okay, this is instead the probability that an individual, a particle, a bumblebee, which is in the state x at the time t, will be at the state u at the time t plus dt. Okay? So again, this is telling me what is the probability for an individual, for a particle, which is in the state x at the time t, to change to b at the state u at time t plus dt. Let me write this. Probability to individual at the state x at time t is instead at state u at time t plus dt. Fantastic. Then actually, one important observation. What if x is equal to u? What does x equal to u would mean for this probability?
There is no change of the states.
Which means that
We are in the first case that individual state between x and x plus x.
no, wait. Okay, it's correct that there is no change in the state. But what's the condition for not having a change of the state? When does the state change?
When an individual encounters
Very good. If my state does not change, what does it mean?
There is no interaction.
That I didn't encounter any other individual. So basically, x equal to u means no encounters. Then instead, if x, of course, is different from u, this means that there was some encounter with another individual particle, call it. Very good. Now, starting from all this information, what we would like to do is to find a evolution equation for f for this function here. Okay, now that I have all this information, I would like to find this kind of evolution equation. Basically, what I will do is something very similar to a conservation law applied, well, more or less applied to this probability that an individual at the state x at time t is at state q at time t plus t. I will use some something which is called the mass action law, which basically tells me that the probability to find a partner, to have an encounter, is somehow proportional to the number of partners. So the probability that I have to encounter somebody which is at the state y must be proportional somehow to the number of individuals, the fraction of individuals which are with state y. Correct? I mean, if I'm brown and you are blonde, and then there are all the other world, the rest of the world, it's everybody is brown, the probability that I have to encounter just one guy which is blonde is smaller, because it should be proportional to the number of people which are blonde. So let me call C the size of the population, total number of individuals. And then this means that the quantity that I can write as f y and t times c times the y. What is this quantity? So remember, what's the definition of f? What's the quantity f times c times the y? This is trivial, eh?
That's the fraction of the population in the state y at time t.
So f times the y is going to be the fraction of the population. Now I'm just multiplying by the population. So what I'm finding is just the number of individuals. This is the number of individuals with the state included in y plus the y at time t. Okay, great. Now, using all these things, I should be able to rewrite the probability f of u t plus dt x and t. Let's see how can I do this then. First of all, in the case x different from u, we say that this would be some probability that comes from the fact that the individual with state x has met somebody. Correct? Because x changed to state u. In order to x change to u means that x encountered somebody. Now, what's going to be then this probability? This probability is going to be equal to, first of all, the probability that x meets somebody with a generic state y, which is given by this thing, right? So this is the probability. The probability that x meets y in the time between t and t plus dt. Okay. Now, how many y's are out there? How many individuals with state y are out there? what's the number of individuals of with state y?
F of yt multiplied by c.
Multiplied by the y, exactly. So this is multiplied by f y t c d y. Okay? There is still one thing which is missing. Remember that I'm looking for the probability of x changing to u. So what I have to do now is to multiply this thing here by this quantity here. So this is the probability that an individual x with the state x that meets another individual with the state y changes to the state u. Now, that's actually not the end of the story. There is another ingredient here, which is the following. I'm defining the encounters of my individual x with the generic individual y. Okay? But what's this y? Well, y can be whatever between the range of possible states that I have. So any y between 0 and 1 would contribute to this probability. So what I have to do here is to integrate between all the possible states between 0 and 1. So that's what I'm doing here. So this part here will take into account the part of this total this function, this distribution, this probability distribution, which is this probability function, which is connected to the fact that the individual x is changing its state because he met some other individual. But we have said that there is actually also the possibility that x does not change its state, correct? We say that if x is equal to u, this means that basically x did not have any encounter with any other particle, with any other individual of the population. What's going to be this other probability? Well, this is going to be the, where is it? Here it is. Probability of no encountering. So the probability of no encountering is given by 1 minus eta of x, y in the t. But I have to remember that this must be true. I mean, I'm considering no encounter with any particle. So I cannot encounter any particle, any y between 0 and 1. So I have to multiply this by the number of particles with the state y, which is again f, y, t, c, the y. And then I have to integrate between 0 and 1. Pay attention that both this integration here, 0, 1, are referred to the y. Okay? This is integrals in the y. So this means that I can put outside the integral the t. So in order for not to confuse, let me cancel this and that, and let me put this outside the t and the t. There is still one small thing missing.
Sorry, prof.
Yes.
One question, but the first integral, the integral of psi, is the sum of all the probability we have seen before? I didn't understand the meaning of the integral of psi, maybe.
The first integral.
Yes. No,
So
no, integral of psi between 0 and 1. Yes, that.
There is no integral of psi.
Psi, x, y, u, and du.
Ah, psi, sorry.
Psi,
yeah,
sorry.
Yeah,
Yes.
yeah, perfect. Well, this is just a normalization. So psi is the probability that when x meets y, change to a some state u. Okay.
Okay.
Now, the states u are u can be any state between 0 and 1. Okay?
Okay.
So if I'm integrating between 0 and 1, this means that I'm integrating on all the possible states u.
Okay.
But what is the probability that x has to change to any other state between 0 and 1? Well, it surely change to some state between 0 and 1. So this probability is going to be, this integral is going to be equal to 1.
Ah, okay, okay. Thank you very much.
It's just telling you that it's changing to some state between 0 and 1.
Okay, okay. Thank you.
Okay. All right, what I was saying, yeah, that the very last thing to be added in this formula is of course delta distribution. You know what's that Dirac delta, right? Delta distribution. You know what does this mean? No, very good. So this is basically a function which is equal to 1 when u is equal to x, and that is equal to 0 otherwise. So this is basically a function that you use to switch on and switch off this term here. So again, you remember that we say that if x is equal to u, this means that there was no encounter with other particles. So the idea of no encounters with other particle is here inside. This formula tells me that there is no encounter. But in order to use this term in this formula, I have also to tell the formula that this term is true only when x is equal to u. And for doing this, I'm using this delta function here. Okay, again, this delta function, delta u minus x is equal to 1 when u is equal to x and 0 otherwise. Okay? Yeah, I'm just waiting for people to settle down. Now, that's not the end of the story. So what we have found is a formula for this probability. Again, our final goal is going to be to find an evolution equation for the function f. Not even for this probability, but for the function f. So our final goal is going to be to find an equation for the time derivatives of f. So what I have to do is to massage a bit this formula in order to obtain some derivatives of the function f. And for doing this, actually, I have to assume. Let me ask you to assume the following two formulas, which I'm not going to prove because otherwise it's going to be a course in Markov processes, and that's not the idea. So these are the two formulas. The first formula, so these are formulas for rewriting this probability here in terms of similar quantities, similar probabilities, and another formula which instead connecting the function f of x and t to a probability like this one. So let me write them. The first formula tells me that the probability that I have that an individual with state u at the time 0 change to the state x at some time t plus dt is equal to the integral between 0 and 1 of fx t plus the t v and t times f v and t u 0 in the v. So let me comment this very briefly. The idea is that I'm multiplying, so this probability is going to be equal to the product of the probabilities that I have to pass from a state u to a state v, and then from this state v to the state x. What I'm doing, I'm then integrating on all the possible v's, and what I will get with this expression is exactly this is an x. The probability to pass from u at time 0 at x at time t plus dt. Okay? I'm just considering the fact that it's possible that I have some intermediate stage, which is this stage v, and then I'm just integrating on all the possible stages, on all the possible states v. And then the second formula is f x q t is equal to the integral between 0 and 1 of f x 2 t 2 x 1 t 1 f x 1 t 1 in the x1. Okay? So I'm gonna use these two formulas to modify a bit this other formula and derive to some evolution equation for the fraction for the function f. Then, all right, let me start by using.
Sorry.
Yes.
We use these two formulas to modificate the last part of.
Everything, all this. So what I'm doing is to rewrite this equation using the two formulas. Okay. More specifically, okay. Let me use exactly the same notation that I have here in the notes. So let me go. This formula here is the formula number 1. This formula here is the formula number 2, and this formula here is the formula number 3. And let me also cancel the delta function because it's disturbing. Nice. Now, what I'm going to do is to write the I'm going to use the equation 1 to write these terms in the equation 2. Well, sorry, this no, just this term in equation 2. So if you see this term here is a probability that the individual at with state v at time t changes to the state x at time t plus the t, which is exactly what is written here. So what you have to do is to call Vx and rename this x u, and that's exactly this formula that you have here. Exactly the same thing. So what I'm going to do is to use this formula to rewrite this term that I have here. And then I get, okay, f x t plus the t u0 is equal to, questo è meglio che lo copio, integral 0 and 1 of what? Parentesi 1 minus the t integral between 0 and 1 of eta v y f y and t c dy times the delta function plus the t integral between 0 and 1 of eta v y f y and t c c v y x dy. And all this thing is multiplying this part here, f v t u 0, everything in the v and integrated between 0 and 1. Okay, so let me repeat. What I've done is to take the equation number 2. So the left-hand side is the same. The right-hand side, what I've done is to write this factor in the integral using equation number 1. All right. Now what I have to do is to do the following: what I have to do is to subtract to the left hand side and the right hand side the quantity f of x and t u naught. So this is left hand side minus this thing and right hand side minus the same thing. And then what I do is take this thing and divide by the t. Okay? Now, what is the left hand side? What's gonna be the left hand side? No. Let me write it explicitly. So this is f x t plus the t u naught minus f x t u naught divided by the t. Nothing? No idea? This is going to be the derivative with respect to time of f xt u naught. Correct? So this is basically a df in the t. Derivative with respect to time of the probability that an individual at state u at time 0 would be at the state x at time t. Now, in the right-hand side, what we have? We have the second term in the integral, so this beast here, which I can directly rewrite divided by the t, and it's giving me integral between 0 and 1 of the integral between 0 and 1 eta v y f y t c psi v y x f v t u naught d v d y. There is probably some mistake here because this is not exactly here. There is a mistake. Sorry, guys. This is x minus b. I was just copying the delta function, but in any case, I renamed the variables in delta functions that is upstairs. So now what do I have here? What I have to do is right. So basically what I have now is the first term, which is integral between 0 and 1 of, let me split in the two parts, delta x minus v times f of v t u 0 in the v. Then I have these other terms, which is minus the t, integral between 0 and 1 of the integral between 0 and 1 of eta v, y, f, y, and t, c, the y in delta x minus v times f, v, t, u, 0 in the v. So basically this is this term here is this one times the delta times the f integrated in the v. The second term is this guy here times the delta times this guy here in the v and the y, because there is an integral here in the y and another integral in the v. And I do not have to forget that I have still to subtract this f of the probability of a state u to be at a state x at time t, f x t u 0, right? Because I subtracted left hand side and right hand side, this thing. This is divided by the t. Okay, this should be good. Is it clear or should I repeat? Let me repeat. Okay, what we have done? What we have done is to rewrite the probability of a particle in state u at time 0 to be at state x at time t plus the t. We are already in this complicated way. Then what I've done? I have subtracted left hand side and right hand side the quantity, the probability of a particle at state u at time 0 to be at state x at time t. So I've subtracted here and there, and then divided by the t. So the right hand side, the results of this the left hand side results in the derivative with respect to time of the fxt u0. The right hand side instead results in a first term, which is this one, which comes from the second line of this equation. And then I have still this other term that I have to massage a bit. Now, what is this? The first integral. The first integral, which is here in parentheses, this integral between 0 and 1 of delta x minus v times this f in the v. Remember what's the meaning of delta. Delta is a function which is equal, delta of x minus v is equal to 1 when x is equal to v, and it is equal to 0 for any other value of x. Okay. But what am I doing here in this integral? I'm integrating on all the possible values of v. So whatever is the values of x, since x is has surely a value between 0 and 1, so whatever is the value of x, I will surely find a v which is equal to x, because I'm integrating between 0 and 1. I'm considering all the possible values which are between 0 and 1 of v. So surely I will find just the point where this delta is equal to 1. So this delta will be equal to 1 exactly when v is equal to x. When v is equal to x, this factor of the integral is going to be equal to f of x t u 0, right? Because remember that delta is equal to 1 only when x and v are equal. And when x and v are equal, I can just write v as x. So the results of this integral between 0 and 1 of this integrand is exactly just this. Is f of xt u naught. So it's the probability that the particle starting with the state u is at time t with the state x. This is the result of all these integral. Usually, this is important, an important formula that you can bear in mind, which is if you are, well, in this case, the domain is between 0 and 1, but let me suppose that you have some domain D on top of which you are defining some delta function in the same way. So what you would have as the integral over this domain of delta x minus x naught times f of x naught is going to be in the x naught is going to be equal to f of x. Okay, because again, that's the x naught equal to x is the only value for which this delta is going to be equal to 1. So the only contribution that we will have to this integral comes from that value, and in that value f of x naught is equal to f of x, because x naught is exactly equal to x. Now, yeah.
Is there a plus between the first and the second line?
Between, you mean here?
Yeah.
Probably yes. We will check it later, but it should be a plus. Yeah, that's a plus. That's a plus. Now, but if this quantity is exactly fxt u naught, well, that's exactly these things here. This is exactly the quantity that we have subtracted on the right-hand side before dividing by the t. So this cancel this. Then what I do is I divide, I still have this term here in this parenthesis, the second term in parenthesis. I can divide the t and the t. Okay. And I can do still one more thing. I can do still one more thing in for this second term here, because as you see, this second term has there's something that has disappeared. This is an integral which contains another time a delta. So it's an integral on the v of delta x minus v times function of v. So this means that I can, sorry, remember that there is this first line. I'm now rewriting only this part. If you want, probably it's better. Let me rewrite everything, because otherwise it's a mess. So then the t f x t u naught now is equal to the first line, integral 0 1 integral 0 1 eta v y f y t c c v y x f v t u naught the v d y. Okay, this is simply, I'm just writing the first line. And then in the second line, we say that the only part that survived is minus integral between 0 and 1, integral between 0 and 1 of eta v y f y t c dy delta x minus v f of v t u naught dv. So what I want to do is to rewrite then this second line, using the fact that it's an integral which contains a delta function. So basically what I can do is to do the integral between 0 and 1 in the V, and this will result, just this part, will result in what? Minus the integral in the y will be there. So integral between 0 and 1 in the y stays like that. Then I have eta of what? X and y. It's correct. That's correct. Eta x and y, right? Because now remember, I'm integrating in the v and I have a delta. So every time that I encounter a v, it becomes an x. I have delta of x minus v integrated on v. So anytime that I have a v, this becomes x. So this eta of I don't remember what was here. It's minus. Let's double integral. Okay. Then they ask me why I prefer the blackboard. So eta x and y times f y t times what happened here? Do provide us nodes. Fine. Yes, I provide the nodes. Yeah. F, y, and t and c. And then what I still have is this f. F, x, t, u, no. Almost done, guys, almost done. Well, almost there.
Sorry.
F of x and t is this one. I just changed the v in x.
Yeah, okay, but why the second integral is not in 1 and 1?
Oh, sorry, it's just because disappeared and I was just, yeah, it was just some. So this is just the second line. I'm just writing the second line. The first line stays as it is. There is still one part missing.
And v became x because I have a delta function, right?
Yes, because I have that, not only but because I have a delta function, because I'm multiplying by the delta function and integrating on the entire space of definition of this function. Because if I have just the delta function, if I have something like this, I cannot see anything. That's actually a function.
Okay.
But then, if I'm integrating over all the space of y, then this thing here is equal to f of x. And that's what happened here, because I'm integrating in the v. So this is delta x minus v, and I'm integrating in the v. All right, now what I have to do is to multiply left-hand side and right-hand side by the fraction fu0. So I'm multiplying the, well, let me wait, left-hand side and right-hand side. I'm multiplying both by f of u0 and then I'm integrating left hand side and right hand side in the u. Now let's see with the left hand side and then the right hand side is just algebra. The left hand side becomes so integral derivative with respect to time of what? F x and t u 0 times f u 0 in the u. Correct? Fu0 does not depend on time. Okay? I'm supposing that all these functions are regular, blah, 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 that the boundary, that the volume does not depend on time, and blah, blah, blah. Everything is very smooth. So the end of the message is that I can put outside the derivative with respect to t. So I can write this thing as derivative with respect to t of the integral of fx t u 0 times f u 0 in the u. This is an integral between 0 and 1, 0, 1, 0, 1. What is this thing? Actually, it's the formula number 3. The formula number 3 is this one. So that's exactly the right hand side of formula number 3. Correct? So basically this integral, what is this integral giving you is fxt. The fraction of the population which has state x at time t. And I have in front the derivative with respect to time. So as you can understand, what this is going to be exactly the evolution equation. So now what I'm doing is to calculate the right hand side, and with the calculation on the right hand side I will have the evolution equation of my system, of my model. Okay? So let me start from the second term. So I have minus integral between 0 and 1 eta x y f y t c f x t u naught. This is multiplied by f, well, this is the y. This is multiplied by f u naught, and is integrated in the u. So remember, right hand side multiplied by f u naught, u0, and integrated in the u. And then I have the second term. Let me start by the first term, and so the second term is going to be what it is? This one, where I have to do the same thing, multiply by f u0, integrated in the u. In any case, again, let me start by this. Second term is the first term. Well, that's the first term, not the second term. So let me start with this part. Okay. So what I'm doing, let me start by doing the integral in the u of fu0 times fxt u0. This is again fxt. fxt. So this is giving me minus fxt does not depend on y, so I can put it outside of the integral. So I have fx and t. And then I have the rest of the integral, which is integral between 0 and 1 of eta xy times fyt times c dy. Okay, so this is the first part. Then let's do the second part, which in this other equation was the first part instead. Then what I have to do is the integral between 0 and 1 and 0 and 1 of what? Eta v epsilon, vy, sorry, fyt, c of vyx, corretto? Sì. fvtu0 dv dy. Now remember that this thing was multiplied by fu0 and integrated in the u. Okay? Again, that's always the same story. So I'm doing the integral in the u. So the integral in the u means that I have to isolate all the factors which are functions of u, which are fu0, fvtu0, integrated in the u between 0 and 1. That's again the formula number 3. That's gonna be again just, well, not again, it's gonna be f of v and t. So it's gonna be the fraction of particles which are at state v at time t.
Sorry, but why now we have 3 integrals?
Because I have the integral in the v, an integral in the y, and another integral which is in the u. So in the other case we had just one integral, because the other integral was basically eaten by the delta. We integrated on the delta and we basically were able to already perform an integral. So now these three integrals, I can do the integral on the u. So this second term, this second part becomes, now I have two integrals, the two integrals in the v and the y. Eta is the same, eta vy. F, y, and t is also going to be the same. Then I have, well, c is a constant. Then I have the probability c vyx. And finally, I have the result of the integral in the u, which is gonna be f of what? What's the result of the integral of in the u of this quantity?
Vt.
F of v and t. So it's the fraction of the population which is at state v at time t. The v, the y. Guys, full stop. That's good. So this formula here is a formula which is called the gain-loss equations, which is a gain-loss for each state x. It's a formula which is telling you how does change with time the fraction of the population with state x. So why it's called gain loss? Because you have a loss in the number of individuals with the state X, which is given by this term here. So basically this term here tells you the individuals which change from the state X to some other state. Gain, the equation is gain loss. This is the loss part. Then you have the gain part, which is this part here, which instead is telling you the individuals from any other state which are changing to the state X. So the fraction of individuals with state X is changing because part of the individuals with state X are changing to another state, and part of the individuals with other states are changing to the state X. This is gain loss equation for state X. And since I'm generous, I think that we can stop here because I think that this was enough heavy for today, probably. Any question or any doubt? Well, in any case, on the lecture notes, this is very badly explained. I mean, on the lecture notes on the book, you find directly this formula without seeing how to arrive to this formula, which for me, I think it's a bit too much complicated for a student to arrive to this formula by itself, by himself. So for this reason, I will post this piece of papers. Speak loudly because otherwise I cannot hear. Hello? Probably. Okay, if there is no question, also there at home, no question.
Sorry, Professor. Is there any source that we could practice this equation somewhere to,
Okay.
yes, remember it, yes.
Okay, so again, what I will do, I think not tonight because I do not have any scanner here, but I will scan my handwritten notes, and I will post for both yesterday and today, and I will put these notes on Teams, for example. Otherwise, what you can do, well, what you can do is to download the original paper which described this model, which in any case it's also a hard paper, so I don't know if you want to do that. But I will put my handwritten notes. In any case, this equation is also commented in the book by Bellomo.
Thank you so much, Professor.
Okay. All right, guys, the lecture is over.
Sorry.
No, that's not over.
We take the original function like a smooth, regular, no.
So usually for this kind of problems, your functions are always well behaved. In applied mathematics, in mathematical physics, it's very rare that you have singular functions. Have you ever observed the singularity in the real world? When you are eating something, do you observe any singularity? No, singularity is somewhere where, some point where things explode and go to infinity. And in most cases, you do not, in most cases of everyday life, you do not find this kind of singularity. Of course, you have systems with singularities. A black hole is a singularity, but otherwise, don't have any kind of singularity. Sorry, a black hole is not a singularity. In the middle of a black hole, there is a singularity.
Sir, I have a question. Apart from this, can you extract the same model for a game probably, which includes winners and losers, maybe for a chess tournament, maybe?
Sorry, I didn't understand. Can you repeat, please?
I was thinking from a practical point of view.
Yeah.
So suppose if we like this model talks about dominance, right? So there's always a winner and loser, right? In this case. So if two interactions happen, am I audible?
If interactions happen?
Yeah. So when this interaction happens, there's always a winner and a loser, right? If I'm getting it correctly.
What I'm not getting is the question. If you can write the question, probably would be better. Can you write down the question, guys? So otherwise, please. Can you write down? Yeah, because otherwise I cannot understand. So what's the problem?
Is there always a winner and loser in each state?
An individual?
In each state when interactions happen.
When interaction happens, yeah.
Yeah. So will there be a winner and a loser?
There will be a winner. Yeah, that's correct. Actually, yes. Actually, you get the problem. This is the problem: winning and losing. Yeah, that's exactly the same.
Okay.
The same problem. Yes.
So,
yeah, sorry,
yes,
I was not understanding. That's very correct. This is actually another way for referring to the problem. Is the winning losing problems. There is always in the interaction, so in the encounter, there will always be a winner and a loser. Basically, this would be encoded in the function psi, x, y, u that you have probability transition to a state u of the individual with state x. That's very correct. Very good observation. Yes.
Thank you, sir. Yeah. Okay. So my question was, how can we can apply this same problem to maybe a chess game, right? Or a chess tournament.
Game.
Chess tournament.
I'm not.
Yeah,
sure.
Because my question is, so if there's a winner and a loser, and the encounters don't happen, like if one wins, he goes to an upper state, and the lower one goes to another state, and two interactions won't ever happen again, right? The interactions won't be repeated, right? So with that, actually, it's just a different approach I'm trying.
Frankly speaking, I do not think that it's exactly the same kind of model that you can apply for the simple reason, because basically this is a kind of statistical model which is taking into account the encounters between many individuals. In the kind of theory of game theory that you want to probably build up, you do not have this kind of interactions in the games, do you? That's actually
I was just it was all about like the encounters won't happen in real life, right? Like these encounters which won't be repeated, right?
Yeah, right.
So so if that happens, and when there's a clear winner and a loser for each encounter, and different states.
Yes.
So by the end of the by the end of the process, I think we can have a clear-cut positions for each individuals, right, with the rank. So that was what I was thinking, sir.
All right. Yeah. Then in this case, from this perspective, eventually you can use exactly the same kind of model. Of course, taking into account the fact that you have to model properly the interaction itself.
Yes, sir. That was the question. Thank you.
Yeah. Anything else? No.
As of now, no, sir. Thank you. Thank you very much.
All right. Okay. Thank you. Cheers, guys. Bye. Ciao.
Arrivederci, prof.
Ciao.
Arrivederci.
Ciao.
Arrivederci.
Buona serata.